Okay, so what I'm going to show you how to do today is a statistical analysis called Anova. Alright, so previous videos have talked about comparing means of two groups. So if you have two groups and you want to compare the means of two groups, you want to use something called a t-test. So you got group A, you got group B, a bunch of numbers. You want to see if there's a difference between A and B in the average value, so you use a t-test. Okay, but let's say you have a different kind of situation. Let's say you're growing some fish in a tank, and what you're interested in is whether or not three different kinds of food will differ in how quickly these fish can grow. Alright, so you got a bunch of fish. Some of them are better drawn than others. Whatever. They're growing in the tank, and you're going to feed them food A, B, and C. Okay, maybe they differ in protein, they differ in fats, who knows. Doesn't matter. We have these three different kinds of food. Okay, now if you wanted, you could do a t-test and compare A and B, then you can do a t-test and compare B and C, then you can do another t-test and compare A and C. For reasons I'm not going to go into here, that is not the proper approach statistically. Okay, you just don't want to do that way. What you want to do is first ask, is there any difference among A, B, and C? So is there any difference across the three different treatments? Okay, to do that we need to do what's called an Anova. An Anova is an acronym that stands for Analysis of Variance, and it's one of the most common statistical tests that you're going to find. There's a variety of different ways to do it, but it's the most common statistical test. Now, what we have then is we have our three aquariums with a bunch of fish in each aquarium, and we're going to measure the growth rates of these fish. Now, here's a little thing. Technically, you don't want to do that. Technically, you would want to have, for food A, B, and C, you would want to have multiple aquaria, each with a bunch of fish in them. Alright, because if you are measuring all the fish in this aquarium and comparing them to that aquarium, then comparing them to that aquarium, you're not really measuring the effect of the food necessarily. Maybe there's something happening with this particular aquarium, and the fish are just happening to grow faster. But then if you spread them out over multiple aquaria, then hopefully that would take care of those sort of random problems. But because this is for generally a undergraduate audience and not a graduate audience, we're going to cheat. We're going to say that you can go with just 3 aquariums, each aquarium with multiple fish, and each fish will count as a single replicate, a single measurement that we're going to make. Okay? Alright, so we do our measurements and we get a bunch of growth rates of these fish. Okay, so what are we going to do? We're going to do our analysis of variance. So remember, what our null hypothesis is going to be there is no difference Remember, because it's a null hypothesis, it says there's no difference. There's no difference in this case, in growth rate, but it'll be whatever metric you're using. In growth rate among foods A, B, and C. The alternate hypothesis would be there is a difference. But this is important. It just means that there is a difference somewhere. It doesn't mean that A is definitely different from B, or A is definitely different from C, or B is definitely different from C. It just means that somewhere there is a difference, and we'll come back to that. Okay, so let's go to Excel. Here we are. We got Excel. We have our these are our data, right? Food type A, B, and C. These are just a bunch of numbers I put. One of the things is we don't have to worry about having equal numbers for each treatment. Okay, so A, B, and C, different numbers each. So first off, let's make a nice figure. Okay, how would we display these? So let's put our headings over here, and let's get the average, the mean for A, B, and C, and I can just click on this column and I copy that. Boom, boom. Those are the means. And I want to get a measure of variance, so let's put our standard deviation. So a standard deviation of a sample for that column. Boom, boom, boom. Okay? Great. What's next? Let's make our figure. So select those, insert. We can insert an XY plot, but let's do a line. Okay? And it doesn't really matter which one we pick, because we're going to be deleting the line. But by using a line, it gives us A, a B, and a C down here on the x-axis. First thing we didn't want to do is we want to get rid of the line in between it. Why do we want to get rid of the line? Because that line indicates that there's some sort of directionality. Okay, so this would be appropriate if this were like time. Okay, but it's not time. These are just three different kind of food things. So we select it. Let's go to Format, Series 1, Format Selection. Come all the way over here. We want line, no line. Boom. Okay, perfect. Then there's all this other junk that Excel likes to give us. Get rid of that chart title. Don't put that there. Get rid of these horizontal lines. Ugly, ugly, ugly. Let's put in a line over here for our vertical axis. Solid line. Good. Okay. Oh, we should make this one match. Solid line. Good. Okay, let's make these symbols bigger. Why? Excel loves to make symbols small, so we'll go over here, marker, and maybe I'll have to cut that part out. Let's make it bigger. Okay, that looks somewhat acceptable. And let's make all of the fonts bigger. So let's just select the entire thing, and then we just come up here and well, that's a little too big, but that looks good. Okay, all right. There's no reason for everything to be so minuscule. But now we would need to add. You know what? I'm going to make these even larger. Okay, let's make them. Whoa, let's make them 3. See how that looks. Okay, good. Now let's add our error bars. So we select these, we go to Format, we go to Design, Add Chart Element, Error Bars, and we want more error bar options. We want them going in both directions, and we want custom value. specify the value. The positive is going to be that. By selecting that, it's going to add that value to each. Negative, it's going to be the exact same. We hit OK. Voila. Beautiful. Okay, so that's our figure. And we would have to add a axis titles, of course. Almost forgot. So format, design, add chart element, axis titles, primary, horizontal. Let's just call it food type. Just food. Why do we have to write food type? And then over here, add chart element, primary, vertical, and this would be growth rate in millimeters per day. Alright, and come on, let's make this, try this down just a little bit. Okay, so let's get to the Anova. So what the Anova is going to do is going to say, is there a difference somewhere among these three values? How do we do our statistics? We go to data analysis. If it's not there, then you're going to need to go to file, options. I'm going quickly through this because I've shown you guys this before, and now I don't remember where it is. It's got to be add-ins. Sorry, add-ins. There we go. Excel add-ins, go. Analysis tool pack, that has to be clicked. Then you hit OK, and data analysis should appear here. Alright, so you click data analysis, and we want, Anova single factor. Now, why is this a single factor and not a two-factor? Well, let me open this back up again. It's a single factor Anova because we have just one treatment, which is food type. So we have food type A, B, and C. And we have lots of replicates, a lot of different fish, but we're just looking at one treatment. Or we could sometimes say one factor. Now we might decide to add a second level. So you might say, okay, I have food type, but what about temperature? Maybe it matters between food type and temperature. So temperature. They did walk by there. All right, so you have temperature, and we can have temperature at, say, 25 degrees, 20 degrees, and 15 degrees. And we have a bunch of fish here. And so in this case, we would actually have 9 tanks, because we have now the treatment of food type and the treatment of temperature. Okay, so that would be a 2-treatment Anova. But that's not what we're dealing with. We're dealing with a single factor or single treatment analysis. Okay, so we want a single factor. We hit OK. Boom. Our input range. You should have all the data next to each other. I'll select all of them there. They're grouped in columns. Labels are in the first row because labels are in the first row because A, B, and C are there. Okay, so input range, columns, labels are in the first row. We want alpha 0.05, just leave it as it is. Output range, I like to stick it in the worksheet, and then boom, here's what we got. This is the output of my Anova. And so you can see here, group A, there's 19 of them. Average matches up here. Variance is something related to standard deviation, but not exactly. It's not the same, but it's involved in the calculations. But you can see that the means match, so that's a good sign. This down here is our ANOVA table. All right, this is the thing that you want to look at to figure out, to test your null hypothesis. We're not going to go into all of these things, but this is called the sums of squares, the degrees of freedom, the mean square. This is the F value. This is the statistic that's important. And this is the P value. All right, so remember the P value. If P is less than 0.05, then you reject your null hypothesis. All right, so this, remember, E means an exponent to the power of 10 to the power. So this is really tiny. It's scientific notation. So this is much less than 0.05. Okay, so what do you do with this information? Because your p-value is so small, you reject your null hypothesis. So how would you write this up? You would say there was a significant difference among the mean growth rates for the 3 food types. Okay, and then what do? You say table 1, and you put this table, leave out the F crit. That's not a standard thing that you put, but you put this table in your paper, and you would say table 1, ANOVA of growth rates for 3 food types. Boom. And then so someone can read this statement in your results. Okay, so you're reading your results, blah, 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 blah. There was a significant difference among the mean growth rates for the 3 food types. Table 1, then they know to refer to table 1 in the results. Here it is, and they look at this p-value and they see the p-value is very low. This is what this means between groups is this is the effect of food type A, B, and C. So there is a difference between the groups. Within groups is just sort of an error measurement. You don't have to worry about what that means. You should learn it eventually, but for our purposes, it doesn't matter. Okay, so there's a difference between A, B, and C. Great. But then you might say, well, it looks like A is bigger than B and bigger than C. Is B different from C? Probably not, but how do we know? Right? We don't want to just guess. So there are a number of ways that you can do this. There are a whole series of tests called post hoc tests, or sometimes a posteriori tests. There's a number that you can do. There's one that I like called Fisher's LSD, which is least significant difference. But there's a bunch of tests that you can do after the fact. So now that you've done one overarching analysis, you can go back and try to figure out which of these groups is different from which. For you guys, the simplest thing is just to do a bunch of t-tests. Now, I told you at the beginning you can't do a bunch of t-tests from the start, okay? But here's the rule. Once you establish that there is a difference overall from the ANOVA, whoops, I gotta learn to spell, then you can do individual t-tests. Okay? If you don't understand why, don't worry about it. Okay? It's a little esoteric. When you take a basic statistics class, they'll tell you why. So let's just do a bunch of t-tests. Data analysis, t-test, unpaired. Let's assume unequal variances. Alright, variable 1. Let's just select all of them. I think that'll be safe. Variable 2. Labels, output range. Stick it over here. Nuts. Okay. Hit OK. Boom. What do we got? Okay, there's A versus B, and you look at the t-test video if you're not sure what's going on, but here we go, two-tailed t-test, and we see that it is definitely significant. Alright, so let's compare A to C. Data analysis, t-test. Let's look at group variable C. Boom. Output range, we got to click on a different location in the, otherwise we'll write over it. Boom. A versus C, also significant. Okay. Boom. Boom. Okay, what's the last one we got to compare? We got to compare B and C. Gut tells me that those are not different, but we still got to test it. So we select B. We already have C. We need a new output range. Put it right there. And our P is not significant. Okay. So what does that mean? That means A is different from B. A is different from C. But there's no difference between B and C. Alright, cool. So what do we do with that information? How do we put that in our paper? So what we might want to have is, let's move this down now, and say we're continuing. There was a significant difference among the mean growth rates for the 3 food types. Type A was significantly, just don't say it was different. Let's use some more information with the same number of words. Greater, or type A had significantly greater growth rates than B or C, and then you can do t-test, and let's put our t's in here. T is equal to 7.289. How many degrees of freedom? 35 degrees of freedom. P is equal to, or let's just put P is much less than 0.01. And let's put another t-test for A versus C. T is equal to 7.740 with rounding. 35 degrees of freedom. And again, P is less than 0.01. Okay, so there was a significant difference in the mean growth rates of the feed. Type A had significantly greater growth rates than B or C. There was no significant difference between foods B and C. Okay, so you can write all that out. Or, if you want, you could make things a little bit simpler. Let's just copy all that, and you say multiple t-tests demonstrated that type A has significantly greater growth rates than B or C, and let's just get rid of all this junk. And there was no, but then we'll refer to our figure 1. There is no difference between foods B and C. Okay. And so now we have to include this nice, beautiful figure that we just drew here. Now what we can do is we can demonstrate the differences between these in a few ways. One way is to insert, so the easiest thing is just to copy this, put it here into put it here in, okay, start that bit over. So the easiest thing is to copy your figure, copy it, paste it here as an image, not as a picture, not as a figure, because then we change things in one and change in the other. And then you can demonstrate that these things are different with lines. So this horizontal line here, and then another horizontal line here, and then what you can do is insert 1, 2, 3 asterisks. So the horizontal line shows things that are not different from each other. So A and B and C are different from each other because they have different horizontal lines, right? There's a break. But B and C do not differ because there's one horizontal line here. And then these 3 asterisks demonstrate how significant the difference is. So 1 asterisk is equal to significance at 0.05. 2 asterisks is 0.01. 3 asterisks is 0.001. So because our data are significantly different, much less than 0.01, we put 3 asterisks. If the difference had been, say, 0.023, then we would put 1 asterisk. If the difference had been 0.004, then we put 2 asterisks, right? Because this is less than 0.05 but greater than 0.01. This is less than 0.01 but greater than 0.001. Okay? So those are standard things that people would use, and then I don't want all that junk there. Boom. There's our figure. Alright, so we did our Anova. Here's our figure, and here is a indication of the significance. Alright, so that's all you really need to know about Anova. You have your data together like this, put together a figure like this, do an Anova table, write your results like these. There was a significant difference, blah blah blah. Multiple t-tests demonstrated that these differences existed. Refer to the table for the Anova, the figure, and then put this Anova table in just like that. Put that figure in like that, and you're done.